Good day everyone, so today our group will be presenting the group assignments of Sta400 Probability and Statistics. Our group 3, will be presenting the set T questions. So these are our team's members. My name is Pamela Amber anak Janice Martin with the matrix number of 2024-207-554 will be presenting the introduction and question 1. As for the introduction, this group assignment is aimed to apply key statistical concepts to real-world situations. The topics covered include binomial distributions, Poisson approximation, normal distributions, and moment-generating functions. Throughout these assignments, students are able to enhance their understandings of statistical and probability concepts. So as for question 1, part A1, in the first part, we are looking at a small sample of 8 plastic items with a 2% defect rate. Since we have fixed number of trials and 2 possible outcomes, defective or not, we use the binomial distributions. So the question asks for at least 1 defect items. To find the probability of at least 1 defect, we use the complement rule 1 minus the probability of 0 defects. This gives us a result of 0.1492. As for the next questions, we look at 7 shipments. Here, a success is defined as a shipment having at least 1 defect sample. Since the question asks for what is the probability that at most 1 shipment will contain at least 1 defective sample. So as for the calculations, we define Y as the number of shipments that contain at least 1 defective sample. So our new N is 7s, and our probability P now is 0.1492, which is from our last steps. We need the probability of at most 1 shipment being defective, which is Py less than or equals to 1. This is the sum of Py equals to 0 and P1 equals to 1. When we put them in a formula, we get P0 equals to 0.3227 and P1 equals to 0.3961. So when we add them together, we get the final results of probability, which is 0.7188. For question 1, A3, the third part, our sample size increased significantly to N equals to 1 to 5 samples. So because of N is large and P is small, the Poisson approximation is the most efficient method. So the question asks for what is the probability that there will be at most 3 defective samples using an appropriate approximation method. As for the calculation part, first we calculate the mean rate, which is the lambda equals to NP. We have our N equals to 1 to 5 and P equals to 0.02. When we multiply them together, we get the answer of 205. We want the probability of at most 3 defects, which means Px less than or equals to 3. This means we add the probability of P0, P1, P2 and P3 together. Using the Poisson formula for each other probability, we get the answer of 0.0821, 0.2052, 0.2565 and 0.2138 respectively. We add them together and we get the answer of 0.7576. So as the final part of question 1, question B, explain the difference between exact binomial and Poisson approximation. Exact binomial is a method of repeating the same experiments a fixed number of times with only 2 outcomes, which are success or failure. The probability will stay the same each time. Meanwhile, Poisson approximation is a method of counting how many times something happens over a fixed time or space, but we don't know exactly. So the events will happen randomly but at a consistent average rate. That's all from me, thank you.
So for the question number 2A, define the moment generating function MGF. So the answer is moment generating function MGF is the function that generates the moments, which is EX, EX squared and EX cubed and EX power of R. Next, for question 2B, let Y be a binomial distribution with N equal to 3 and P equal to 0.4. So the first domain, derive the moment generating function MGF of Y, MYT. So first of all, we need to write it in binomial form. So y binomial 3, 0.4, because we know that the n equals to 3 and while p is equal to 0.4. Next, the function of binomial is 3 choose y, p power of y, and in the bracket 1 minus p power of 3 minus y. And we know that the value of y is 0, 1, 2, 3 because it states that n is equal to 3. So the moment generating function MGF of y is equal to sum of e power of ty multiplied with the function of binomial just now, which is 3 choose y, 0.4 power of y, and 0.6 power of 3 minus y. We know that the p value is 0.4 while the 1 minus p is equal to 0.6, which is 1 minus 0.4 is equal to 0.6. And then after that, we substitute all the value of y, which is 0, 1, 2, and 3. So the final answer is 0.216 plus 0.432 e power of t plus 0.288 e power of 2t plus 0.064 e power of 3t. So next, for the question 2b2 Roman, use the MGF to find the first and second moments. We know that the first moment is the first derivative of the MGF. So we differentiate first the MGF and we get the answer is 0.432 e power of t plus 0.576 e power of 2t plus 0.192 e power of 3t. And that is not the final answer. We need to substitute the value of t with 0. So the final answer we get for the first moment is 1.2. And next, for the second moments, we need to find the second derivative of the MGF. So we get 0.432 e power of t plus 1.152 e power of 2t plus 0.57 e power of 3t. And same as just now, we need to substitute the value of t with 0. So the final answer for the second moment is 2.16. For question 2c, suppose that k has the probability density function fk equal to 1 over 4 e power of negative k over 4 where k is more than 0. Find the moment generating function of k and kt. So we know that probability density function means it is continuous function. So how we want to find the moment generating function, we need to integrate it. So moment generating function of k is equal to integrate 0 to infinity e power of tk multiply with the function of fk, which is 1 over 4 e power of negative k over 4 dk. So we put out the constant first, which is 1 over 4 outside the integrate. Next, we arrange it so it will become e power of negative k, because we know that if e power of negative infinity, it will become 0. So we need to arrange it to become e power of negative k and in the bracket 1 over 4 minus t. And then we integrate it. So the final answer for moment generating function of k is equal to 1 over 1 minus 4t. For question 2c2 Roman, find the ek minus 1. So first of all, we need to find the ek, which is mean. So find the first derivative of moment generating function. We get 4 in the bracket 1 minus 4t close bracket power of negative 2. So if we want to find the ek, we need to substitute t with 0. So we get the answer is 4 for the ek. The question asks us to find the ek minus 1. So ek minus 1 is equal to ek minus e1. So ek, we find it just now, is equal to 4 while E1 is equal to 1. So 4 minus 1 is equal to 3.
For the question number 3A, on average the number of visitors to an internet website are 30 visitors in a given day. Find the probability of the website receiving between 25 and 32 visitors inclusive in a given day. Use the normal approximation. Okay, for number 3 part A, the average number of visitors per day is 30. Since this follow a Poisson distribution with a large mean, we use the normal approximation. So the mean is 30 and the standard deviation is square root 30, which is approximately 5.48. We are asked to find the probability that the number of visitors is between 35 and 32 inclusive. Using continuity correction, this becomes 24.5 less than equal to x less than equal to 32.5. Next, we convert these values into z-scores. For 24.5, the z-score is -1, and for 32.5, the z-score is 0.46. Using the standard normal table, the probability between -1 and 0.46 is 0.5185. Therefore, the required probability is 0.5185. Question 3B, an engineering professional body estimates that 75% of the students taking undergraduate engineering courses are in favor of studying statistics as part of their studies. If this estimate is correct, what is the probability that more than 780 undergraduate engineers out of a random sample of 1000 will be in favor of studying statistics? Okay, for part B, we are given that 75% of students are in favor of studying statistics with a sample size of 1000. This is a binomial distribution, but since the sample is large, we use the normal approximation. The mean is equal to 750 and the standard deviation is 13.69. We are asked to find the probability that more than 780 students are in favor. Applying continuity correction, this becomes x more than 780.5. We then calculate the z-score, which is 2.23. From the standard normal table, the probability of z being greater than 2.23 is 0.0129. Hence, the required probability is 0.0129. Question 3C. A soft drink machine is regulated so that it discharges an average of milliliter per cup. The amount of drink is normally distributed with a standard deviation equal to standard deviation milliliter per cup. If 33% of the cups contain less than 193.4 milliliter of drink and 5.48% of the cups contain more than 224 milliliter of drink, calculate the value of mean and standard deviation. Okay, for the last part, part C. For part C, the amount of drink per cup is normally distributed with mean and standard deviation. We are given two probability statements. First, 33% of cups contain less than 193.4 milliliter, which corresponds to a Z value of negative 0.44. Second, 5.48% of cups contain more than 224 milliliter, meaning 94.52% contain less than 224 milliliter, which correspond to a Z value of 1.6. We then form two equations using the Z-score formula. Solving these equations simultaneously, we obtain the standard deviation is 15 milliliter and the mean is 200 milliliter. Therefore, the mean amount of drink per cup is 200 milliliter and the standard deviation is 15 milliliter. In conclusion, this presentation has demonstrated the applications of fundamental statistical concepts across questions 1 to 3. We explored different probability distributions and statistical methods to analyze real-life situations, including discrete and continuous random variables, normal approximation, and the use of standard normal distribution tables. Each question highlights the importance of selecting appropriate models, applying correct assumptions, and interpreting results accurately. Overall, these solutions show how statistical techniques can be effectively used to solve practical problems and support data-driven decision-making.